Okay students, this is the fourth part of sets. Last part I started a concept of Venn diagrams, how to draw the Venn diagram for different situations, how to name the shaded regions. Okay, so yesterday's problem is, last problem is 7th one. So the shaded region named by A minus B union B minus A, or A union B minus A intersection B. This is called symmetric difference between two sets. Okay, so today also I want to continue Venn diagrams concept. So today's next Venn diagram is 8th one. This is universal set. This is set A, this is set B. Okay, this color are not good. Now I will use another color. Okay, observe students, except A union B, everything is shaded except A union B. You want to give the name for that, A union B. What happened? U minus A union B. From U, A union B is removed, no? What is U minus A union B? A union B whole complement. With the definition of complement, U minus K means K complement, no? U minus A union means A union B whole complement. Okay, next 9th. So this is universal set. This is set A. This is set B. This is universal set. Okay. Here I want shade except A intersection. Everything I want shade except A intersection B. What is the meaning of that? From U, A intersection B is removed, just like. Okay. That I can write U minus A intersection B. That is nothing but A intersection B whole complement. Okay. Next one, 10th one. 10th onwards some more difficult situations, no? Because we will take 3 circles. 3 are overlapping circles, A, B, C, and this is a universal set. So this is important. The shaded region, don't think that is A intersection B. That is not A. That totally the intersection B. The shaded is not A intersection. That is said to be only intersection B. The dotted point, see here, this is A intersection B. So what I shaded is, this is A intersection B, only intersection B. From A intersection B, something is removed, no? That's why that is not called A intersection B. That is called only A intersection B. Only A intersection B. Or sometimes I can write A intersection B intersection C complement. Okay. So important thing is, how can you say that the shaded region A intersection B intersection C complement? How can you prove? So I will prove you. See, take a bigger circle. First of all, shade A intersection B with one color, shade C complement with another color. Their intersection should find. What will get the area? That is nothing but A intersection B intersection C complement. This is set A, set B, set C. First of all, I want shade A intersection B with one color. The green color I used for A intersection B. Next I will shade C complement. What is the meaning of C complement? Except C, everything should shade. Except C, everything should shade. Okay, not good color, Nana. I don't like this. Wait. Not good color. Except C, we want shade everything. See, I am using red color horizontal lines. Those the region is for A complement, C complement, C complement. Except C, observe, except C, everything is shaded in universal set. Okay. Now observe, horizontal lines represented for C complement. Another color is a green color, that is represented for A intersection B. What do you want between them? What do you want another intersection you want? Find intersection of those two. What will get? That portion only, no? So I will show you with another color. So this portion only, no? So that's why A intersection B intersection C complement is nothing but only A intersection B. Yeah, okay, should next 11th one. What is that? B intersection C. Only B intersection C shaded now. I can say only B intersections in that one. Only B intersections. Only B intersection C. Or B intersection C intersection A complement. Okay. Similarly, you can shade only intersection C also. Next 12th one. Important one. Yeah. This is for universal set. I can say it's very important. This is set A, this is set B, this is set C. Okay. Observe students. Yeah. The shaded region. Not A, none that one, not A. Part of A shaded. So what I can say, this point belongs to A, but this point also belongs to A. But difference is, second point is belongs to both A and B, but first point is belongs to only A. Only A. That's why the shader is named by only A. I can write only A. Or in other words, A intersection B intersection B complement intersection C complement. Okay. So how will get this means again now you need to draw shade A separate color, B complement intersect C complement another color, then we'll get the result. That's not a big problem. 13th one now. Yeah, this is A, this is B, this is C, this is U, C. Except A union B union C, everything is shaded. Except A union B union C, everything is shaded. So what I can say now that one, that is nothing but U minus A union B union C. U minus A union B union C. Or in other words, I can say that A union B union C whole complement. Next. Yeah. Results in sets. Important results. Several results are there, no? Complement law, associative property, commutative property, like that. Some important results I will write. Okay. First one is De Morgan's laws. De Morgan's laws. We have several De Morgan's laws. First of all, I will explain two, Nana. One of them is A union B whole complement equal to A complement intersection B complement. Second is A intersection B complement equal to A complement union B complement. But how to prove these things? How can you prove that A union B whole complement equal to A complement intersection B complement? How can you prove that A intersection B whole complement equal to A complement union B complement? How to prove? That is important. So we have several two methods are there to prove things. For example, you want to prove that set A equal to B. So one of the way is element wise proof. Element wise proof means we want to prove that every element of A is in B. Okay, and every element of B is in A. By the definition of equality of two sets, I can say that set A equal to set B. Here also, for example, A union B whole complement is taken as set P, and A complement intersection B complement taken as set Q. We want to prove that P equal to Q means it is enough to prove that every element of P is in Q and every element of Q is in P. This is called element wise proof. But to prove element wise proof, we need a concept that is called statements. That concept is not there in our book. So that's why I want to use another alternate methods to prove the things in set theory. That is called Venn diagrams method. Okay. In Venn diagrams method, we need to prove all these things. So I will show you what I will explain you how to use Venn diagrams method to prove the things in set theory. For example, you want to show that set A equal to set B by using Venn diagrams. So it is enough to prove that the region represented by set A equal to area of the region represented by set B. Okay, for example, this is set A, this is set B in Venn diagram. It is enough to prove that there should have equal in areas. Then I can say that set A equal to set B. So things you should prove by using Venn diagrams means we want to show that the areas represented by the set should be equal. So first of all, I want to prove the first one. A union B whole complement equal to A complement intersection B complement. After proving this, you people can clearly understood how we can prove things in set theory by using Venn diagrams. Okay. First of all, first one, A union B whole complement equal to A intersection A complement intersection B complement. LHS. What is LHS? A union B whole complement. Okay, students, this is a Venn diagram. By using this Venn diagram, I want to prove here this is the universal set nana, and two circles are taken. Okay. Yeah, observe here. This is set A. This is set B. Both are circles only. Yeah, this is also same. No, these two figures have equal areas. Second part is A complement and B complement. This is A and B and universal set. Observe, A and B are congruent circles. B and B are congruent circles. Union and union are congruent circles. By using areas concept, I want to prove that these two are equal, means LHS part equal to RHS parts. First of all, A union B whole complement should find area that represented by A union B whole complement. Means you want to shade the area which is represented by A union B whole complement. Means U minus A union B. You want to take a region which is U minus A union B. See, I am shading now. Okay, from U we need to remove A union B. What is left? That is called A union B whole complement. So the shaded region is represented by A union B whole complement, or shaded region area is represented by A union B whole complement. I will write now this area. Okay. Okay. This area is nothing but A union B whole complement. Yeah. This is taken as part 1. Similar here also, you want to show that the area should be equal to A intersection A complement intersection B complement. For that, first of all, what should do, Nana? First of all, you want shade A in A complement. Next, you want shade B complement. Their intersection should find. Okay. So I want shade A complement. To shade A complement means from U you want to remove A. From U you want to remove A. That's all. So, yeah, see what I am doing now here. From U, A is removed now. Except A, everything is shaded. So what I can say, the shaded region is nothing but A complement. I will write. Okay. Yeah. The dot, this color is meant for A complement. I will write A complement. Next, B complement. From mu you want to remove B, you need to use another color. So I want to use vertical lines to represent B complement. I am shading Nana by the help of vertical lines. Except B, everything should shade. Okay. The vertical lines represented by B complement. Okay, I will write vertical line for B complement. What next? You want the intersection. Intersection means the intersection of the green color and the vertical lines. So same, no? Same what you got in equation, that only you are getting, same area. Okay, that's why I will write A complement intersection B, A complement intersection B complement equal to this area. So, which is same as part 1. This is taken as part 2. somewhere I want write, so I will rub this, later I will write now. So from one end to I can say that A union B whole complement equal to A complement intersection B complement. Okay. So in this way you can prove the things in set theory. One of the De Morgan's law proved by using Venn diagram. Now I want to prove another De Morgan's law. Okay. I think you people understood, na? Second De Morgan's law. Again same diagram I want to use on here. Okay. Yeah, this one first diagram for LHS, second diagram for RHS. So I wanted second De Morgan law, that is A intersection B whole complement equal to A complement intersection, A complement union B complement. Intersection becomes union, union becomes intersection. This is set A, this is set B, universal set. This is set A, set B, universal set. First of all, I wanted LHS nana. LHS what? A intersection B whole complement. Okay. So same procedure. Now we need to shade A intersection B whole complement, or you want to find a area represented by A intersection B whole complement. So except A intersection B, everything should shade. Okay. Except A intersection B, everything is shaded. Okay, I will write down. This color is meant for A intersection B whole complement. Now I want to write area sense. Okay, area. What area it is representing? Yeah, except this everything. Okay. Second, RHS. A complement union B complement. First of all, shade A complement with one color, shade B complement with another color. After that, you need to find union, not intersection, union. First of all, I want shade A complement. A complements, you want to remove A from U minus A. Horizontal lines. I am using horizontal lines. With the help of horizontal lines, I am shading A complement. Okay, this is meant for A complement. I want to use another color for B complement. So B complement, vertical lines, red vertical lines. Using red vertical lines, I want identify B complement, mu minus B. Except B, we need to shade. Okay. Yeah. Okay, I will mention. This is represented for B complement. Important students, what happened? Union you want. Union means horizontal, vertical. Intersection means grid portion you want, but here union, no. You want total shaded portion, except that white portion, everything. So that is A complement union, B complement is nothing but except that everything. Observe, no, both are giving same area. This is 2, this is 1. So from 1 and 2, what I can conclude? A intersection B whole complement equal to A complement union B complement. Student, this is very important concept, and by using a Venn diagram concept, you can prove everything. So third, De Morgan's law, that is A minus of B union C equal to A minus B union, intersection A minus. Union becomes intersection. Fourth one is A minus of B intersection C. Intersection becomes union. A minus B union A minus C. In this way you can remember. So these two are also De Morgan's laws. These two are also important. You people can prove, that is not big problem. By using three sets, here 3 sets are involved, A, B, C. By using these 3 sets, by using Venn diagrams, you can prove these things. For LHS, one separate diagram. For RHS, one separate diagram. We want to show that the areas are equal. Okay, first of all, shade B union C. After shade A, subtract them. What you will get, that should be equal to A minus B intersection A minus C. Okay, you people can prove. Okay. Yeah, next thing is distributive laws. Distributive laws. Students, our first distributive law, A union B intersection C. Remembered as C. Observe, A union B intersection A union C. This is one of the distributive law. Another words I can say that union is distributive over intersection. Already you know that, no? A of B plus C. Yes, in real numbers I can say A of B plus C equal to AB plus AC. This is called distributive law. So what you call here multiplication is distributive over addition. Here union is distributive over intersection. This is one distributive law. Second distributive law. So A intersection of B union C is equal to A intersection B. A intersection B union A intersection C. These two are known as distributive laws. Now I want to prove these distributive laws. How can you prove distributive laws? By using Venn diagram. That is important. Generally element wise proof is there, but I don't want to use the element wise proof. So we need concept of statements. That's why I am using Venn diagrams to prove these things. How to prove this distributive law? So we need to show that area of this set equal to area of this set by using Venn diagrams. Okay, I will show you. Listen. Okay students, my first distributive law I want to write here, that is A union B intersection C equal to A union B intersection A union C. I want to prove this by using Venn diagrams concept. This diagram is for LHS, that is A union of B intersection C. So this diagram for RHS, what is that, Nana? So A union B intersection A union C. Okay. Yeah. To find the area represented by A union of B intersection C, first of all shade B intersection C. After shade A, the union should find B intersection C. I want shade B intersection C. So this is A, this is B, this is C, the union side B intersection C. So I want shade B intersection C with the black colored horizontal lines. I will write here what is that. This is for B intersection C. Now I want shade A with another color, red colored horizontal lines, red colored vertical lines. This is for A. I will write here only. Yeah. Now what you want, intersection or union? Intersection is grid portion, but you want union. No? Union means total shaded portion. I will show you where is that total shaded portion. This total shaded portion. Observe students, this total shaded portion, just like coconut shape. This total shaded portion is represented by A union of B intersection. That I will write. A union of B intersection C is represented by this portion. Okay, this portion. Okay, yeah, this portion. Now you want to show that the area represented by A union B intersection A union C also, that coconut shape. Then you can say that these two sets are equal. Okay, so this is A, this is B, this is C, this is universal set. First A union B should shade. A union B should shade. So A union B, I want shade A union B. So this is A union B. Yes students, A union B shaded. So I will write here what is that. A union, this color is represented for A union B. Next I want shade A union C with another color. A union C. So this for A union C. What do you want? Intersection means this color and this color intersection you want. Observe Nana. Clearly I can say the portion is nothing but again same red color and green color intersection. So this one only same. That same. Therefore this I can say this is 1. So what I will get here Nana? A union B intersection A union C is nothing but again coconut portion only. So my diagram is not correct. Okay. So this is 2. From 1 and 2 you can say that these two are equal. I will write here. Yeah, somewhere. So here only I will write from 1 and 2. 1 and 2. So this happens. Similar way you can prove this second distributive law also. Intersection of B union C. Okay, second distributor also we can prove, but so in this diagram I want to prove. Observe here. Time is completing. The second one is A intersection of B union C equal to A intersection B union A intersection C. So here LHS parts I want to take LHS. This is LHS, that is A intersection of B union C. This is RHS, that is A intersection B union A intersection C. So first of all I want to shade B union C with one color. Okay, B union C. First of all I want to label now. This is A, this is B, this is C, universal set. This is A, this is B, this is C, this is universal set. B union C, B union C. Okay, students. Yeah, the shaded one is B union C. I will write. So sorry, I want to use that color also. Okay, this color is for B unions. Next I want shade A. Okay. A. This is for A. What do you want? The intersection you want. Intersection of these two means what, Nana? This one only, no? This portion only. This portion is intersection. I will write. So A intersection B union C area is nothing but this. This is taken as first part. Second part. Here A intersection B should shade A intersection B. So this is A intersection B. I will write here. This is A intersection B. Next we need to shade A intersection C. A intersection C. This one A intersection C. This is A intersection C. What do you want? Union or intersection you want? Union. Union you want means total shaded portion. Same. Total shade, this one only, total shaded portion. That's why I will write Nana. A intersection B union A intersection C area is nothing but this one only. Same. This is 2. From 1 and 2. Actually, at last you need to write. So I will write here now. From 1 and 2. From 1 and 2, we can conclude that A intersection of B union C equal to A intersection B union A intersection C. Students, these are very, very important laws. So this approach is important. Proving the laws in set theory by using Venn diagrams. That's why John Venn is introduced these Venn diagrams or logical diagrams or set diagrams. Okay. Students, the next concept is cardinal relation between sets. Cardinal relation between sets. So this is also another important part, Nana. Cardinal relation between sets. Yes, students, already I explained what is the cardinal number of a set. For example, A is a one set, n of A represent number of elements that presented in the set A. That is cardinal number. For example, A is given as 1, 2, 7, 9. What is n of A means I can say n of A equal to 4. But in Venn diagrams, how can you define cardinal number? That is important. For example, the set is given. For example, this is a set. What is n of A? What is meaning of n of A? In general, what you can say that how many dots are there in n of A? How many points are there in n of A? So actually, this region, no, you get infinitely many points. Assume that only finite number of points. Okay. So n of A means how many dots are there in the set A? That is nothing but n of A. So observe students here. This is set A given. Venn diagram sense, Venn diagram like this, Venn diagram. So n of A stand for here, yeah, 1, 2, 3, 4, 5, 6, 7, 8 like that. Now we want to establish the relationship between sets. If two intersecting sets are given, for example, A and B are two intersecting sets. This is set A, this is set B, A, B. Always universal set should exist, no? If sets are there means automatically universal set will be. So this is a universal set U. Okay, first result is n of A union B equal to dash, n of A union B, number of elements presented in the set A union B. You need to find what is the relation. So through example I will explain. For example, here 2 dots, here 1 dot, here 2 dots, here 3 dots, here like that 3 dots are given. So in general, what I can say, n of A union means 1, 2, 3, 4, 5, 6, 7, 8. 8 I can say 8. Okay. Another words I can say n of A union B is equal to n of A minus B. N of A minus B is these 3 points plus. So students, A minus B is not a real number, but n of A minus B is a real number. Should take care. Okay. Yeah. A minus B plus n of B minus A. N of B minus A. Number of elements which are present only in B. That is 3. Plus n of A intersection by I can write. Number of A intersection by I can write. Number of elements which are presented in both A and B. That is 2. Observe 3 plus 3, 6 plus 2, 8. Correct only. No? That's why n of A union B now onwards treated as n of A minus B plus n of B minus A plus n of A intersection B. I will write this. Yeah, first cardinal relation, n of A union B equal to n of A minus B plus n of A intersection B plus n of B minus C. Should remember this is important. One result. Second result, listen all of you. N of A union B, another way I want count. Another way, see, n of A elements I will count first, plus n of B elements I will count. N of A means what, Nana? 1, 2, 3, 4, 5. Plus n of B means what? 1, 2, 3, 5. Total how much? 10. But actually, what should get? 8 only. Why you are getting 10 means these elements are counted 2 times. N of A plus n of B. 2 times counted. 1 time you need to subtract minus n of A intersection B. Okay, that's why n of A unit B means n of A plus n of B minus n of A intersection B. Okay, students, that's why here this is A and this is B. I want n of A union B, number of elements which are present in A, total A union B. So what number of elements present in A first plus number of element present in B. So what happened? So this area is counted 2 times, no? That's why you need to subtract 1 time. That's why n of A union B equal to n of A plus n of B minus n of A intersection B. So this is another cardinal relation. Okay. So third cardinal relation, n of A minus B, or sometimes I can say n of only, that is A intersection B complement. What is that? How many elements? 3 elements are there. What is that? N of A minus n of A intersection B. Similarly, fourth one also, n of B minus A you want. So that is n of B intersection A complement. That is nothing but n of B minus n of A intersection B. Okay. So by using Venn diagrams, Nana, you can solve so many problems.